Hello. In the next 8 slides, I'm going to try to describe how to do substitution of equations and Gaussian elimination for those students who don't recall or never learned how to do it. The first method is substitution. To do substitution, you take one of the equations and you write it so that one variable is on the left-hand side and the other variables are on the right-hand side. It's easier when you have a problem that has zeros where there's no I2 term like the second equation or the third equation where there's no I1 term. It's easier to do substitution with these sets of equations because they're simpler. But it wouldn't matter if they were non-zero. You can still do it. You just write I1 on one side and I2 and I3 on the other side. So in this example, I'm going to take equation 3 and I'm going to rewrite it as I2 equals negative 2I3 plus 1. You can see that I2 is equal to negative 2I3 plus 1. Then I'm going to take that equation and substitute it for I2 in the first two equations. In the second equation, it actually doesn't matter substituting it because it's multiplied by 0. So it doesn't change equation 2. But in equation 1, substituting I2 equals negative 2I3 plus 1 leaves equation 1 with just two variables, I1 and I3. So you get I1 plus 2 times negative 2I3 plus 1 plus 3I3 equals 3. This is equation 1. This simplifies in the end to I1 is equal to I3 plus 1. And again, there's no change to equation 2 from this substitution. So I did one substitution and I ended up with an equation that has I1 in terms of I3. Previously, I had an equation that had I2 in terms of I3. Now, if I take this equation that has I1 in terms of I3 and I substitute it into equation 2, I get 2I3 plus 1 plus 4I3 equals 2. 2I3 plus 2 plus 4I3 means I have 6I3 and 2 on each side, which cancels. So I end up with 6I3 equals 0. Therefore, I3 is equal to 0. If I take that I3 equals 0 and I go back to the substitute equation, that means that I1 equals 1 and I2 equals 1. So for my two substitute equations, I1 and I2 equals 1, I3 equals 0. And I've solved the problem. It's a little more work if these were not 0, but it works just as well. Take one equation, create a substitute for one variable, plug it into the other two. Take one of those other two equations, and you'll only have two variables. Find one of them in terms of the other, and then substitute it into the equation you did not modify. And you'll end up with one variable and a solution. Then you back substitute to find the solution. So it's a little more work, but not much. That's the method of substitution. The array method. So this is Gaussian elimination, and I have a Wikipedia link to Gaussian elimination. You take those same equations and you put them in an array form. And in array form, you have 1I1 plus 2I2 plus 3I3 equals 3 volts. 2I1 plus 0I2 plus 4I3 equals 2 volts. 0I1 plus 1I2 plus 2I2 times I3 equals 1 volt. It's a little bit out of the scope of this course to show you how to do the linear algebra on this, but you're literally taking this column and multiplying it by this row, this column by this row, and this column by this row, by the third row, to get values 3 volts, 2 volts, and 1 volt. Now, once you have it in the array form, you can write the augmented matrix. The augmented matrix is this matrix, 1, 2, 3, 2, 0, 4, 0, 1, 2. And then right alongside of it, we put the right-hand side column vector, 3 volts, 2 volts, and 1 volt. And this is called the augmented matrix. We're now going to solve the augmented matrix using row rules, just row manipulation. There's 3 row manipulations we're allowed to use. I'll go over them on the next page. And we're going to create, by doing those row manipulations, a row echelon form where the upper diagonal is 1 and below it is zeros, The second element in the diagonal is 1, and below it is zeros, and the third element is 1, and the elements below that are zeros. In this scenario, this can be reverted back or converted back to the matrix form here, and you can see that if you have 0 and 0 and some number that's 1 here, that means that I3 is equal to whatever's on that side with the units appropriately converted. I'll walk through that in a second. So I mentioned that essentially what I did here is I created a matrix, 3 by 3 matrix of resistances. So I wrote this in bold to indicate that they're arrays. Array R times column vector I is column vector V. And the augmented matrix is R and V essentially. But those actual elements don't matter. This is the system of equations. The system of equations works for any types of equations. These are the 3 row operations you're allowed to perform. You can swap any row. You got to swap the whole row, but you can swap any 2 rows. You can multiply any row by a constant, and constant can be positive or negative, and you can add it to the other rows. And you can replace those rows with that multiplier after you've added it. And you can multiply any row by a constant and then just leave it in that row. So for example, I'm going to take row 1, and my goal is to put zeros below this first column. So I'm going to take row 1 and multiply it by -2 and add it to row 2. So I take -2 and I multiply each term in this row by -2, and I add it to each term respectively in row 2, and I get -2 times 1 plus 2 is 0. -2 times 2 plus 0 is -4. -2 times 3 plus 4 is -2. And -2 times 3, which is -6, plus 2 is -4. So that single row operation does not change row 1 or row 3, but it changes row 2. That gives me row echelon form as far as the first column is concerned. To treat the second column, I'm going to either eliminate the 1 by multiplying -4 by 1/4 and adding it, or I'm going to eliminate the -4 by multiplying 1 by 4 and adding it up above. And that's what I'm going to do. I'm going to take the entire third row, multiply it by 4, and add it to the second row. Later I can just swap the rows. Remember, rule 1 is I can swap rows. So that'll give me a row echelon form more quickly. So I'm going to take 1, 2, and 1 and multiply by 4, add it to -4, -2, and -4. 1 times 4 minus 4 is 0. 2 times 4 is 8, minus 2 is 6, and 4 times 1 added to 4 again is 0. So let's see that over here. So I took 1 times 4, added to -4, and I got a 0. I took 2 times 4, which is 8, added it to -2, and I got a 6. And I took 1 times 4, added it to -4, and got a 0 again. That's multiplying row 3 by 4 and adding it to row 2. And here's the resulting row 2. And then I'm going to swap row 2 and row 3. And this is almost a row echelon form, except that this is 6. I could leave it as 6. This value is 0, but I'm going to multiply it by 1/6. And now it has the value of 1. And if I rewrote this matrix here, which I did, that matrix times I1, I2, and I3 is now 3 volts, 1 volt, and 0 volt. So this is a simplified version of the original set of equations. And the nice thing about this is when you multiply through I1 times 0, I2 times 0, I3 times 1 equals 0, that tells you that I3 is 0. And then if you substitute that I3 is 0, here I have I2 plus 2I3 equals 1. So that tells me that I2 is equal to 1. And I1 is also equal to 1. So just substituting them backwards. If you're doing this manually, that's the easiest way to do it. And I never changed the units. So this is still over here, ohms times the amps equals volts. So I end up with I1 equals 1 amp, I2 equals 1 amp, and I3 equals 0 amps. And that's doing it manually. Many calculators will solve for a mode called reduced row echelon form. They'll also do row echelon form, but if they do reduced row echelon form, that's even better, because then you don't have to back substitute, which is another opportunity for an error. If you can get it into row echelon form, reduced row echelon form, that's where the zeros below the diagonal, where there's all zeros below the diagonal, but also above the diagonal. And so when you do that, your I1 is directly the value in this column, or I3 is C3, I2 is C2, and I1 is C1. And if you did that, you would find out you don't have to do any conversion. So reduced row echelon form is easier. And these calculators will do reduced to row echelon form, and I have notes at the end of this presentation, links to calculator YouTube videos that will help you figure out how to do that. Also, most of these same calculators that will do reduced row echelon form will invert a matrix. An inverse matrix is a matrix that if you multiply by itself using matrix multiplication, you'll get the identity matrix, which is just ones on the diagonal. So if you have R as a matrix times I as a column vector equals V as a column vector, and you multiply by R inverse on both sides, you end up with I equals R inverse times V. And you can directly then find I. And that's how I do it on my HP 48. And that's how some students do it on their TI 84s and 89s, though reduced row echelon form is an option in every case. I think lastly, before I show you the links for calculator help, I want to mention that the equations here were a form of a resistance matrix times a current vector equals a voltage column. But the circuit equations don't have to be all the same. They can be mixed types. So you can have an equation that's a Kirchhoff's current law where the terms of the first equation are all amps. And then you could have two voltage equations where the terms of the equations are volts. Now you notice I still have current variables, but in this case, it's negative some I1 amps, negative 4 amps plus I3 amps, and then in KVL equation I have 12, and this is actually ohms, times I1 amps plus 8 ohms times I3 amps. These units are voltages. I didn't show the ohms, and I should have, but the equations can be mixed. So in this equation, I did fill in the units down here. You can see that the matrix form actually has units of ohms and units that are unitless. And I should have put volts here by Vx, but I did not. Watch your units, but the problem here would solve the same way as we did previously using substitution methods or reduced row echelon form or matrix inversions. And finally, here are links to calculator help. You can click on these links, or you can go to notes under D2L, and under notes, the first document there has these same links.